There are galaxies we can see today that no message from Earth will ever reach. Their light has crossed billions of years to arrive here. It enters our telescopes as evidence that those galaxies exist, or at least existed when the light began its journey. We can measure their redshift, estimate their distance, study their stars, and place them inside a map of the observable universe. But the map creates an illusion. Visibility feels like access. It is not. Some of the objects in our deepest images are already beyond the region where any signal we send now could catch them. Even if that signal moved at the speed of light, even if we aimed it perfectly, even if our civilization survived long enough to wait for a reply, the expansion of space would carry the target away faster than the message could close the distance. Nothing is malfunctioning. No engine is too weak. No civilization has failed. The barrier is built into the geometry of the universe. This is the cosmic horizon, and it divides reality in a way that is easy to underestimate. On one side are places that may still exchange cause and effect with us. On the other are places that remain visible only because we are receiving old light from a past that can never answer. The distinction sounds technical until we follow it to its conclusion. The universe may contain regions filled with galaxies, planets, and perhaps intelligent observers, all of them physically real, all of them once part of the same connected cosmos, yet permanently removed from our future. We may watch their ancient light arrive for billions of years, while losing the ability to influence anything we see. The night sky is not simply a picture of distant space. It is a record of relationships that are disappearing. To understand why, start with a familiar limit. Light does not travel instantly. When we look at the moon, we see it as it was a little more than a second ago. The sun appears roughly 8 minutes in the past. Nearby stars arrive years late. Distant galaxies arrive millions or billions of years late. That delay creates the observable universe. We can only see regions whose light has had enough time to reach us since the early universe became transparent. At first, that seems like the only boundary that matters. Beyond a certain distance, light has not arrived yet. Inside that distance, the universe appears available to observation. But expansion changes the problem. Galaxies are not moving through space in the ordinary sense, like debris flying away from an explosion. On sufficiently large scales, the distance between unbound regions increases because space itself expands. The farther apart two regions are, the more expanding space lies between them. This means a sufficiently distant galaxy can recede from us faster than light without violating relativity. Nothing is locally outrunning a beam of light. The space separating us is growing while the light moves through it. A photon aimed toward us can spend part of its journey losing ground. In the early universe, some light now reaching Earth was emitted from regions that were then receding so rapidly that the light initially moved away from us in terms of overall distance. It still traveled locally toward Earth, but the expansion between us increased faster than the photon could overcome it. Only later, as cosmic conditions changed, did the photon begin to make net progress. This is one reason cosmic distances resist ordinary intuition. A galaxy's present distance, the distance it had when it emitted the light, and the path traveled by that light are not the same number. The universe changes while the signal is in transit, and the change is not slowing toward a final balance. Current observations indicate that the expansion of the universe is accelerating. The cause is described through dark energy, a name for whatever is driving this large-scale behavior. We can measure its effects. We do not yet understand its underlying nature. That uncertainty matters, but the measured consequence is already enough. If accelerated expansion continues, then more galaxies will cross a boundary beyond which signals emitted today can never reach us. Their future light will be stretched, weakened, and eventually pushed to wavelengths so long that detection becomes effectively impossible. They will not vanish all at once. They will fade through redshift, as if the universe is gradually erasing its own evidence. A useful comparison is a message sent upstream on a river. If the current is slow, the message can make progress. If the current matches its speed, it remains suspended. If the current grows stronger downstream, there may be a point beyond which the message can never return, no matter how long it travels. Cosmic expansion is not literally a river, but the consequence is similar. Light always moves at light speed locally. Yet the changing structure of space can determine whether that light ever arrives. The disturbing part is that there is more than one horizon. There is a boundary to what we can observe now. There is another boundary to what we could ever observe, even in the infinite future. And there is a boundary to what we can influence with a signal sent today. These boundaries do not coincide. A galaxy can be visible but unreachable. Another region may be invisible now, but visible later. Some events may eventually enter our observable history, while others remain outside every possible future observation. The word universe encourages us to imagine a single connected arena. Physics gives us something more fractured. What we call the observable universe is only the portion of reality linked to us by past light. It is not a guarantee of future contact. It is not a map of possible destinations. It is not even a permanent inventory of what future astronomers will be able to see. It is a temporary archive, and the archive is closing. This raises a question that reaches beyond travel. Suppose a civilization appears in the remote future, after accelerated expansion has carried nearly every distant galaxy beyond detection. Its astronomers may see only the gravitationally bound remnants of their local group. The wider cosmos could appear static, limited, and almost empty. The evidence for the Big Bang, cosmic expansion, and the large-scale structure of the universe may be faint, inaccessible, or gone from practical observation. They could live inside the same universe we do, and inherit less evidence that the universe ever had a beginning. Their physics would not be less intelligent. Their instruments might be far more advanced, but reality would give them fewer clues. That possibility changes the meaning of a horizon. It is not merely the edge of our reach. It may be the edge of what can ever be known from a particular place and time. We often treat ignorance as a temporary condition. Something better instruments will eventually reduce. The cosmic horizon introduces another kind of ignorance, one created not by human weakness but by causality itself. There may be facts about the universe that are real, nearby on the largest scales, and permanently unavailable to us, and some of them may already be leaving. The idea that the universe has an edge has appealed to human intuition for centuries. An edge sounds concrete. Reach the boundary, look beyond it, and discover what lies outside. The cosmic horizon offers no such opportunity. It is not a wall. It is not a shell surrounding the observable universe. There is no location where a spacecraft could arrive and find a sign announcing the end of accessible reality. The horizon exists because information has limits. Every observation begins with something carrying information from one place to another. Usually, that messenger is light. Every image from a telescope, every spectrum revealing the chemistry of a distant star, every map of the early universe depends on photons completing an unimaginably long journey. Those photons obey the same physical laws everywhere. They never receive special permission to travel faster because the destination is important. They simply move through space, while space itself continues to evolve. That distinction produces one of cosmology's most counterintuitive consequences. Looking farther into space also means looking farther into time. When astronomers point instruments toward galaxies whose light has traveled for more than 13 billion years, they are not observing mature galaxies similar to our own Milky Way. They are examining an earlier chapter of cosmic history. The farther the light has traveled, the younger the universe appears. For a long time, this relationship encouraged an optimistic assumption. As telescopes improved, perhaps every era of the universe would eventually become visible. Build larger mirrors, Increase detector sensitivity. Wait patiently for fainter signals. Technology certainly expanded our view. Space observatories have revealed galaxies from remarkably early epochs. Measurements of the cosmic microwave background allow us to study conditions only a few 100,000 years after the Big Bang. Modern cosmology has transformed what once seemed permanently hidden into measurable science. Yet every improvement eventually encounters the same obstacle. No telescope can collect photons that never arrive. This is where observational astronomy becomes inseparable from the structure of space-time itself. Suppose an advanced civilization possessed a telescope the size of an entire solar system. Every mirror segment aligned perfectly. Every detector operated at the fundamental limits allowed by quantum mechanics. They observed continuously for millions of years. Even such, an instrument could not record light, prevented by cosmic expansion from ever reaching its location. The limitation is no longer engineering. It is causality. That difference matters because history repeatedly teaches us that apparent limits often disappear. Mountains become tunnels. Oceans become shipping routes. Diseases become manageable. Planets become destinations for robotic explorers. Human experience encourages confidence that barriers eventually yield to better tools. The cosmic horizon belongs to a different category. No improvement in propulsion changes it. No increase in computing power removes it. No artificial intelligence predicts information that never enters the observable record. There is another subtle consequence. Astronomers often speak about mapping the universe. The phrase suggests a project with a natural endpoint, as though enough observations will eventually complete the picture. But maps require access. Our largest cosmological surveys resemble something else. Imagine reconstructing an entire continent from a handful of fading photographs drifting toward you across an ocean whose width increases every second. Each photograph captures a different moment. Some depict landscapes that no longer exist. Others arrive distorted after an unimaginably long journey. Many regions never send a photograph at all. Yet from these incomplete fragments, researchers infer the geometry, composition, and evolution of the largest structures ever studied. The achievement is extraordinary. The incompleteness is unavoidable. That incompleteness becomes even more profound when we consider intelligence elsewhere. The search for extraterrestrial civilizations usually assumes distance as the primary challenge. Perhaps another civilization exists thousands of light years away. Communication would simply require patience. Cosmology introduces another possibility. Two civilizations may survive indefinitely and still remain forever unable to exchange even a single message. Not because one becomes extinct, not because neither wishes to communicate, because expanding space-time gradually removes the causal connection between them. There could be observers asking questions remarkably similar to ours, while occupying regions already destined to remain permanently isolated. From our perspective, they are part of the universe. From the perspective of future communication, they might as well belong to another reality. This changes how isolation should be understood. Isolation is often imagined as emptiness. The cosmic horizon suggests something far more unsettling. Isolation can exist inside abundance. The universe may contain staggering numbers of galaxies. Beyond our local region, many may possess planetary systems. Some may host chemistry as rich as Earth's. Others may even have produced intelligence through entirely different evolutionary histories. Their existence is compatible with everything modern cosmology tells us. What becomes uncertain is whether any exchange of information remains physically possible. Distance alone is not the deciding factor, time is. Every year that accelerated expansion continues, another portion of the universe slips farther beyond meaningful interaction. The process is gradual enough that no observer notices it in daily life, yet relentless enough that its cumulative effect reshapes the future of astronomy. This realization also reframes one of humanity's oldest ambitions. Exploration has always implied that unknown territory can eventually become known. Cross the sea, climb the mountain, launch the probe, build the larger telescope. Behind each effort lies the assumption that ignorance shrinks when curiosity persists. The horizon does not reject curiosity. It simply refuses to negotiate with it. Some questions remain open because evidence has not yet been collected. Others remain open because no future evidence can ever arrive. Recognizing the difference may be one of the most important intellectual shifts in modern cosmology. The universe is not merely larger than our ancestors imagined. It contains regions that are permanently disconnected from every decision our civilization will ever make. And if that is true for us, an equally uncomfortable possibility follows. Perhaps our own observable universe is only one small island inside an ocean whose full geography no observer, anywhere, can ever assemble into a complete map. The idea that some parts of reality are forever inaccessible becomes even harder to accept when we remember how often science has overturned apparent impossibilities. For centuries, the Milky Way was mistaken for the entire universe. Then astronomers discovered that the faint spiral nebulae scattered across the night sky were not clouds inside our own galaxy. They were galaxies themselves, each containing hundreds of billions of stars. The universe expanded overnight, not physically, but conceptually. Later came another shift. Edwin Hubble's observations revealed that those galaxies were receding from one another. Space was not static. It was changing. The universe had a history. That discovery suggested an optimistic pattern. Every generation inherited a larger universe than the one before it. Every technological leap exposed another layer of reality. It is tempting to believe the pattern will continue forever. The cosmic horizon suggests otherwise. The limitation is not temporary ignorance. It is built into the structure of space-time. Ironically, some of the strongest evidence for this conclusion comes from light that has already traveled farther than almost anything else we can observe. The oldest light in the universe is known as the cosmic microwave background. It does not originate from stars or galaxies. It comes from an era roughly 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely through space without being scattered by a dense plasma of charged particles. That ancient radiation fills the sky in every direction. Its temperature differs by only tiny fractions of a degree from one region to another. Those minute variations became the seeds from which galaxies, clusters, and eventually planets emerged. Without this radiation, modern cosmology would be almost unrecognizable. It provides a snapshot of a universe astonishingly young compared with the one we inhabit today. Yet even this remarkable window has limits. We cannot simply observe farther back using electromagnetic light because the earlier universe remained opaque. Photons were trapped in a hot plasma long before the microwave background was released. The universe itself blocks our view. Perhaps future observatories will study other messengers. Gravitational waves generated during extremely early cosmic events may one day reveal conditions inaccessible to light alone. Neutrinos preserve information from earlier stages than photons can. These possibilities remain active areas of research, but they do not eliminate horizons. They merely move them. Every messenger has conditions under which it can no longer carry usable information. Every observational method eventually encounters a boundary imposed by physics rather than engineering. That realization transforms an ordinary scientific question into a philosophical one. When we describe the universe, are we describing reality itself, or only the fraction reality permits us to examine? The distinction is subtle. Most scientific theories assume that the laws measured here also apply elsewhere. This assumption has proved remarkably successful. Spectra from distant galaxies reveal familiar atoms, gravity-shaped structures across enormous distances. Nuclear physics predicts stellar behavior with extraordinary accuracy. Consistency encourages confidence. Yet consistency is not completeness. There may exist regions forever beyond observation that obey the same laws. There may also be phenomena that remain hidden simply because no information about them can ever enter our observable region, l'esprit. Science is comfortable with uncertainty. What science cannot do is measure the permanently unmeasurable. That boundary often creates misunderstanding. When cosmologists discuss the observable universe, they are not claiming that nothing exists beyond it. They are identifying the region from which information has reached us since the universe became transparent. Beyond that lies territory whose existence is strongly implied by current models. Its contents remain unknown. This distinction matters because public imagination frequently treats the observable universe as though it were the universe itself. It is almost ternary cosmology, while still involving open questions about its deepest mechanisms, provides us one strength in which the universe beyond our museum can be one larger than the region we can observe directly. Current evidence strongly supports an early period of rapid expansion, though the full details remain under active investigation. If that picture is broadly correct, then our observable universe resembles a single illuminated neighborhood inside an expanse whose full scale cannot presently be measured. The numbers become difficult to visualize, not because they are large, because they cease behaving like ordinary distances altogether. 1 billion light-years already exceeds everyday comprehension. 100 billion changes little emotionally. Eventually, quantity loses meaning. The true divide is no longer between large and small. It is between accessible and inaccessible. Consider two observers separated by an immense cosmic distance. Each constructs careful physical theories. Each maps nearby galaxies. Each detects the cosmic microwave background. Each concludes that the observable universe surrounds them. Both are correct. Neither occupies the center of existence. Each sees only the region causally connected to their location. Their observable universes overlap only if their separation is sufficiently small. Increase that separation enough, and the overlap shrinks. Increase it further, and the overlap disappears completely. Each observer studies a different window onto the same underlying reality. Neither can verify the other's observations. Neither can exchange results. Each develops cosmology, using evidence unavailable to the other. The universe has not fragmented, information has. This possibility carries an unexpected consequence. Scientific knowledge itself may become local, not because physical laws differ from place to place, because the observable evidence available to different civilizations may differ forever. One civilization might infer structures another can never detect. Another may witness astronomical events permanently hidden from the first. Both could follow flawless scientific reasoning. Both could arrive at incomplete descriptions because reality presented different evidence to each. Objectivity survives. Completeness does not. The more carefully we examine the horizon, the less it resembles a distant boundary. Instead, it begins to look like a filter. Not filtering matter, not filtering energy, filtering knowledge itself. And if knowledge depends upon which signals are permitted to arrive, then the future history of every civilization may be shaped as much by the information the universe withholds as by the information it reveals. If the cosmic horizon defines what can be known, another question follows, almost immediately. Has it always existed? The answer is both yes and no. There has always been a limit imposed by the finite speed of light. Every observer occupies a particular moment in cosmic history, and every observation depends on information having enough time to arrive. But today's horizon is not the same horizon that existed billions of years ago. The universe has been rewriting its boundaries from the beginning. Early in cosmic history, gravity played the dominant role on the largest scales. Matter slowed the expansion. Galaxies were still separating, but the process was decelerating compared with what would come later. Then something changed. Around 5 billion years ago, the balance shifted. Observations of distant Type Ia supernovae revealed that cosmic expansion was no longer slowing. Instead, it had begun to accelerate. Independent measurements from the cosmic microwave background and the large-scale distribution of galaxies reinforced the same conclusion. Whatever dark energy may ultimately prove to be, its influence has become the defining feature of the universe's long-term future. This discovery altered far more than predictions about distance. It changed the fate of information. Imagine standing on an enormous frozen lake. At first, every drink drips apart slowly. Walking can still close the distance between groups. Communication remains possible. Now imagine the ice itself begins stretching beneath your feet. The farther apart two people become, the faster the ice expands between them. No one is running. No one is choosing to leave. Yet eventually the stretching becomes so dominant that even walking at maximum speed cannot reduce the separation. The analogy is imperfect, but it captures the central idea. The problem is not motion through space. The problem that the stage itself refuses to remain fixed. This distinction explains why discussions of faster-than-light recession often create confusion. Special relativity forbids any object from moving through its local region of space faster than light. General relativity allows space-time itself to evolve. Those are different statements. Every galaxy sees nearby physics behaving exactly as expected. Local measurements never reveal light being overtaken by another object. Only when enormous distances accumulate does the expansion of space produce recession rates exceeding the speed of light. There is no contradiction because nothing locally breaks relativity. The geometry changes, and geometry determines destiny. For civilizations separated by sufficient distance, the future gradually loses shared events. Suppose an extraordinary supernova explodes in a remote galaxy tomorrow. If that galaxy has already crossed the relevant horizon relative to us, the light from the explosion will never arrive. From our perspective, the event never enters history. It happened. Its consequences influenced nearby stars, planets, and perhaps living observers. Yet within our observable record, it does not exist. History itself becomes observer-dependent. This idea feels uncomfortable because we instinctively associate reality with accessibility. If something happened, surely someone can eventually witness it. Cosmology quietly removes that assurance. The universe permits events that are perfectly real while remaining permanently absent from our future observations. That absence also accumulates. The local group of galaxies, bound together by gravity, will remain intact despite cosmic expansion. The Milky Way and Andromeda are expected to merge billions of years from now, creating a larger galaxy surrounded by a small family, gravitational companions. Everything farther away follows a different path. Galaxy clusters beyond our local gravitational neighborhood continue to recede. Over immense spans of time, they become fainter. Their light stretches into longer wavelengths. Signals weaken. Eventually, even the background evidence for their existence becomes extraordinarily difficult to detect. The process is gradual enough that no human lifetime notices it. Yet cosmology deals comfortably with billions and trillions of years. Against those timescales, the transformation becomes dramatic. Picture an astronomer living 100 billion years from now. Their galaxy contains countless stars. Planets still orbit. Physics continues to operate. Perhaps advanced observatories circle black holes or inhabit artificial worlds built around long-lived red dwarf stars. Their technology may surpass ours beyond imagination. Yet when they point telescopes outward, they discover almost nothing beyond their own galactic environment. No nearby galaxies, no expanding cosmic web, perhaps no detectable cosmic microwave background. Its radiation stretched so severely that practical observation becomes nearly impossible. Without those clues, the modern story of cosmology becomes extraordinarily difficult to reconstruct. The expanding universe may appear instead as a single isolated island surrounded by darkness. The irony is difficult to ignore. Future scientists could possess greater intelligence, more advanced mathematics, and instruments beyond anything humanity has built. Still, they may have less evidence than Edwin Hubble, not because they failed, because the universe erased the records before they arrived. Knowledge, in this sense, has an expiration date. Certain discoveries become possible only during particular epochs of cosmic history. We often speak about living in an ordinary age. From the perspective of cosmology, that assumption deserves scrutiny. Humanity exists at a time when the universe still preserves multiple independent clues about its own origin. Expansion remains measurable. The microwave background remains observable. Distant galaxies still illuminate the large-scale structure of space-time. These conditions need not last forever. Some researchers have described the present era as unusually favorable for cosmological observation. That does not imply humanity occupies a privileged place in creation. It suggests something more restrained. We may inhabit a brief observational window. If that interpretation is correct, then our generation inherited an opportunity unavailable to many who came before us, and potentially inaccessible to many who come after. The universe has not only a physical history, it also has an epistemic history, a history of what can be discovered, and those two histories are beginning to separate. The expansion of space is no longer merely changing the positions of galaxies. It is determining which truths remain recoverable and which disappear beyond every future investigation. If the cosmic horizon limits what can be observed, it also forces us to reconsider one of the oldest assumptions in science. Can every true statement about the universe, at least in principle, be tested? For centuries, the answer appeared to be yes. Perhaps the experiment would require better instruments. Perhaps it would take generations. Perhaps the necessary technology had not yet been invented. But there remained an underlying confidence that reality was, eventually, available to investigation. Modern cosmology has become more cautious. Some questions are difficult because our measurements are incomplete. Others may remain unanswered because the universe itself withholds the evidence needed to distinguish between competing explanations. This distinction appears repeatedly in contemporary research. Consider the overall shape of the universe. Current observations indicate that space is remarkably close to geometrically flat. Measurements from the cosmic microwave background, large-scale galaxy surveys, and other cosmological probes consistently support that conclusion. Yet, close to flat is not the same as perfectly flat. The observable universe samples only a finite region. If curvature exists on scales vastly exceeding our horizon, its effects may be too subtle for us ever to measure directly. The universe could extend indefinitely. It could possess an enormous but finite geometry. Both possibilities remain consistent with existing evidence. The difference may lie beyond observational reach. Inflation presents another example. The theory successfully explains several major features of the observable universe, including its large-scale uniformity and tiny fluctuations that later form galaxies. Many versions of inflation also predict regions extending far beyond what we can observe. Some even suggest that inflation may continue elsewhere, producing an enormous collection of causally disconnected regions with different histories. These ideas remain active subjects of theoretical investigation. What makes them scientifically challenging is not simply their ambition. It is that much of the predicted structure may never become observable from our location. The debate therefore shifts. Researchers no longer ask only whether an idea is mathematically elegant. They ask whether any measurable consequence could distinguish it from competing models. The horizon becomes part of the scientific method itself. It determines which hypotheses remain testable and which drift toward philosophical interpretation. This is not a weakness of science. It is one of its greatest strengths. Science recognizes the difference between uncertainty, created by insufficient data, and uncertainty, created by inaccessible data. The two demand different levels of confidence. That discipline prevents speculation from quietly becoming accepted reality. Yet it also reveals something unexpectedly unsettling. The universe may possess features forever beyond experimental confirmation, not because scientists lack imagination, but because causality denies access. There is another consequence that receives far less attention. Civilizations often measure progress by the expansion of knowledge. Libraries grow, observatories improve, computers become more capable, maps become more complete. The expectation is almost instinctive. Tomorrow's understanding should exceed today's. Cosmology introduces a remarkable exception. Progress is not guaranteed if the available evidence itself diminishes. Imagine inheriting a library where one page disappears every century. Future scholars become more skilled, more disciplined, and more creative than those who came before. Yet each generation begins with fewer surviving records. Eventually, the greatest obstacle to discovery is no longer intelligence. It is missing information. The accelerating universe behaves in a surprisingly similar way. It does not destroy local knowledge. It gradually removes access to distant evidence. Future observers may reconstruct extraordinary detail about nearby stars, planets, and black holes, while remaining unable to recover the broader history that humanity can study today. Knowledge becomes asymmetric across time. This possibility gives our current era unusual significance, not because humans occupy a privileged position, not because history revolves around our civilization, simply because we happen to exist while multiple, independent windows into cosmic history remain open at once. The expansion of galaxies can still be measured. The relic radiation from the early universe still fills the sky. The large-scale distribution of matter still preserves traces of ancient physical processes. Those independent clues reinforce one another. Together they allow cosmologists to test models with a rigor impossible if only one line of evidence survived. Lose enough of those clues and certainty weakens. Not through intellectual failure, through cosmic timing. This raises an uncomfortable possibility. Some of the deepest discoveries humanity makes may never be rediscovered if our civilization disappears. A future civilization emerging billions of years from now could become technologically magnificent, while lacking observational access to evidence we once considered fundamental. Their scientific method would remain sound. Their conclusions would follow from the data available. Yet, the universe would present them with a different puzzle. The realization carries an unexpected emotional weight. We usually fear forgetting because memory is fragile. The universe forgets for another reason. Its expansion changes which memories remain physically recoverable. Entire chapters of cosmic history slowly retreat beyond every possible archive. The night sky does not merely evolve, it edits itself. And that leaves one final question. If horizons determine not only where we can travel, but also what we can ultimately know, then perhaps the greatest limitation facing any civilization is not its technology, its lifespan, or its intelligence. Perhaps the greatest limitation is the universe's quiet decision about which conversations between distant parts of reality are still allowed to continue and which have already ended forever. Every civilization eventually reaches a moment when it asks the same question. How much of reality can ever be known? For most of human history, that question seemed temporary. Every century replaced old boundaries with new instruments. The invisible became measurable. The unreachable became observable. The unknown steadily retreated. The cosmic horizon suggests that this pattern was never guaranteed. It may simply have been the fortunate circumstance of living during a particular era in the history of the universe. That possibility becomes clearer if we stop thinking about the horizon as a line in space and begin thinking about it as a property of time. There was a universe before galaxies existed. There will be a universe after nearly all galaxies, beyond our local group, disappear from view. Neither universe is less real than the one we inhabit today. Yet each offers a profoundly different amount of evidence about its own history. Reality does not remain equally transparent across cosmic time. It opens. It reveals. Then slowly, it closes again. This changes the way we should interpret one of astronomy's greatest achievements. When we measure the age of the universe, trace the distribution of dark matter, detect the relic radiation left from its earliest observable moments, or reconstruct how galaxies assembled over billions of years, we are not merely accumulating facts. We are reading records that will not remain equally accessible forever. There is a tendency to imagine scientific knowledge as permanent once discovered. In truth, knowledge survives only if evidence survives, and civilizations survive with it. Neither outcome is guaranteed. Suppose humanity disappears before preserving everything it has learned. Millions or billions of years later, another intelligent species evolves somewhere within the gravitationally bound descendants of the Milky Way. They develop mathematics. They invent spectroscopy. They discover relativity and quantum mechanics. Eventually, they ask where everything came from. Their investigation begins honestly. Their reasoning is rigorous. But when they search the sky, they encounter a universe unlike ours. No nearby galaxies reveal expansion. The cosmic microwave background has faded beyond practical detection. The large-scale cosmic web has vanished from observation. The clues that allowed 20th and 21st century cosmology to flourish have become inaccessible. From the evidence available, they may conclude that their galaxy is essentially the entire universe. It would not be an irrational conclusion. It would be the best explanation permitted by the data. The uncomfortable implication is not that they would be less intelligent. It is that intelligence alone cannot recover evidence that no longer exists within causal reach. For generations, science has celebrated a simple principle: nature is understandable. Modern cosmology still supports that principle, but with an important qualification. Nature is understandable only to the extent that nature continues to provide evidence. The universe is under no obligation to preserve every clue indefinitely. There is another perspective that emerges from this realization. Humanity often measures significance by physical scale. We compare ourselves with galaxies, black holes, or the age of the cosmos, and conclude that our place must therefore be insignificant. The horizon invites a different comparison, not one based on size, one based on opportunity. Our civilization occupies a narrow interval, during which multiple independent records of cosmic history remain simultaneously available. That does not make humanity central to the universe. It does make this moment scientifically unusual. Whether we are capable of using that opportunity wisely remains an entirely separate question. Perhaps that is the deepest lesson hidden inside the horizon. The universe is not merely limiting where we can travel. It is shaping which questions future civilizations will even think to ask. A society that never observes distant galaxies has little reason to search for cosmic expansion. A society that never detects relic radiation may never imagine a hot early universe. Entire branches of knowledge depend on evidence arriving at precisely the right moment in cosmic history. Discovery is not determined solely by curiosity. Curiosity also depends on what reality chooses to reveal. This is why the horizon deserves to be understood as more than an astronomical concept. It is a boundary between possible histories, between questions that can still be answered and questions that eventually lose the evidence required to answer them, between observers who inherit a richly documented universe and observers who inherit only its remaining fragments. The horizon is often described as the edge of the observable universe. That description is accurate. It is also incomplete. It is equally the edge of future conversation. Beyond it are galaxies whose ancient light may continue arriving, while every possibility of reply has already vanished. Beyond it are events that will occur without ever becoming part of our history. Beyond it may exist civilizations that will never know we existed, just as we will never know whether they asked the same questions beneath entirely different skies. The most unsettling consequence is not that the universe is larger than we can observe. Cosmologists have accepted that for decades. The more difficult idea is that reality itself may contain truths permanently separated from every observer by the ordinary operation of physical law. Not hidden, not forbidden, simply unreachable. Perhaps the greatest mystery is no longer whether the universe has an edge. It is whether every intelligent civilization eventually discovers that knowledge itself has one, and if every civilization reaches that realization in complete isolation, the silence of the universe may not be the absence of observers. It may be the consequence of Horizon ensuring that each observer, no matter how advanced, can witness only one small chapter of a story that no one will ever read in its entirety.